Hello YouTube. Today we are learning how to do insertion sort. So insertion sorting algorithm, we're going to implement it to sort a array of integers in ascending order. So here's a shuffled deck of cards that is unsorted. The way insertion sort works is how a lot of people play cards. They will have how they sort the card decks when they're playing cards. They'll have some numbers and any number on the very left unit, and then they'll, let's say, look at the very last element of the array, this 2 right here, and they will take it all the way to the left side and put it in a sorted position on the left side. So here on the left side, for now, we'll just treat the first card on the left as the left side. So that first card is 4. And we're going to put 2 over it. We're going to put 2 to the left of it. We're going to put it in its appropriate position with respect to what the left side is. So now you can say we have a left side of these 2 cards. We know that these 2 cards are sorted. And we're ignoring the third card for now. So now we're going to take the last card on the deck again, and we're going to find its position, that it belongs in the very left side, which now is 2 cards, and we compare it to 4. Well, it is less than 4, so when you compare it to the next previous element on the left side, we compare it to 2. It is less than 2, so we're going to insert it left of 2, and we repeat this process. Now our left side is composed of 3 elements, and we're going to look at the last card on the deck. That's 6. We're going to compare it to the rightmost element of the left side, that's 4. We know that 6 is greater than 4, so what we want to do is insert it onto the right of 4. So now our left side, our sorted portion of the deck, consists of 4 cards. So now let's take the very rightmost element, that's 3. We're going to compare it to the rightmost element of the left side, that's 6. It's smaller than 6, so we're going to go over one more element, compare it to 4, it's less than 4, so now we're going to compare it to 2, it's greater than 2. So when we're trying to insert a card and we're comparing it, from in descending index order, once we find the first element that is less than the element we're inserting, we're going to put it into one position to the right of that element that was less than the one we're inserting. And right now, just visually explaining it casually, it's very easy to insert items. When we code it up, however, it's a little bit harder, and we'll get to that in a couple minutes. So now we have the last element we need to sort. The 5 elements on the left are in sorted order, such that for each card index I, and let's say an array called A, for each index I from 0 to a dot length, which in this case we'll say A is 5 so far. For each I in from 0 to a dot length minus 2, we have that A sub I is less than A sub I plus 1. So we're kind of jumping the gun here. That's really more relevant to later on in the algorithm, but I'll just write out what I wrote. A sub I is less than A sub I plus 1. And really we mean the index I, the ith index of A array, but we're just going to use math so you can say sub. So A sub I is less than A sub I plus 1, and we're saying this is true for all i's in the set of numbers from 0 to I minus 2. So at this point, you might be wondering why I said I minus 2. And the reason is, let's say we have 5 cards right here. The length of this array is 5. So if we're trying to compare, let's say, the 4th, using natural numbers, the 4th number to the 5th number, well, let's not use natural numbers. Let's use, programmer indexes where we start at 0. So this is the 0th element. This is the 1st. This is the 2nd. This is the 3rd. This is the 4th element. we're trying to compare the third element to the fourth element. Then obviously the indexes for those are 3 and 4. And if we have, length of 5, then this I number right here, in our last comparison, like this is comparison right here, in our last comparison, the third and fourth indexes, we're going to use index 3 and 4. So if this were I minus 1 and we used 4 and 5, we get an index out of bounds error. Certainly the last two elements we can compare are 3 and 4 with I starting at I minus 2. And this shouldn't be I minus 2. This should be N minus 2, where N is a dot length. All this was sort of a tangent though. That will be used later though. That's gonna be something called our loop invariant. Anyway, so going back on the course of topics, we have this last element right here. We need to figure out where to insert it. So we start looping at the last index of our sorted portion of the array. Our last index is 4. So we compare this element right here. We'll call this x. We compare x to a sub 4. If x is less than a sub 4, we're going to go to the next comparison. And x is less than a sub 4. So let's go to the next comparison, which is comparing x to a sub 3. This is the third element of the A array. So is x less than a sub 3? No, it's not. So going back to the previous rule we kind of casually said earlier, we know we need to insert x to the position right of a sub 3. So we're just going to insert it right there. And that's how you kind of colloquially explain it. But now we need to write it out in more programming terms. And the thing we really need to do is how does the insert part work? There's more to meets the eye. So let's go to our code right here. This isn't part of the official function. We're going to write our actual function name right here. So we're going to do this kind of a pseudocode with JavaScript syntax. Here's insertion sort. JavaScript usually does camel case, but we're just going to insertion sort on array A. And we're going to assume we're just not going to worry about any index out of bounds errors yet. So essentially what we're doing is we start with the sorted portion of the array and we start with the unsorted portion of the array. First off, the unsorted portion of the array was literally, well, the sorted portion of the array we said was the left side, and the left side is first of length 1. So first we're saying the sorted portion is literally just the subarray from index 0 to index 0, and the unsorted portion is the rest of the array. Looks like we lost our fourth element. Yeah, there's a fourth element. Okay. And what we're doing is we are taking the element at the index position 1 higher than the greatest index of the sorted portion, and then we are inserting that into the sorted portion. So I guess the way we write that is we're going to have some sub module, some sub function called insert. And that's going to take it's going to take an integer, and we're going to call that m. And it's going to, that's an index, and then it's going to take a value an integer value called x, and that's going to be the actual value of the card. So we're essentially saying we're going to this function calling a function. The way we would call this function is by saying, insert 0, 4, meaning let's insert the element 4 into its appropriate position in the subarray with the index ending at position m. Meaning we have some subarray. Right now it's that we just length 1 with one element 6, and we are going to insert the element 4 into the correct position of there. So let's define how this insert subfunction works. To define how it works, let's kind of make up a more complicated example. Let's say we already have we have an array that's a bit longer. Let's say it is 1, 5, and 6, and we're inserting 4 into it. So when we shuffled our deck of cards, we literally just said, let's have 1, 5, and 6 here. We literally just kind of said insert 4 into there, and we just put 4 in there and then move these ones to the right. The way we'd have to write them in a sort of array syntax is right now 1, 5, and 6 are positions 0, 1, and 2, and 4 is at like position 3, or it really can just be anywhere, it doesn't matter. So we're going to say 4 into a temporary variable called x. So 4 is a temporary variable called x, and then it's kind of represent where these are in the array spots. Right here, it's the array spot index 1, index 2, index 0, index 1, index 2, index 3. We'll just say it's empty right now. So we're going to shift over the 6 value up 1 index to index 3. I'm going to shift over the 2 value, the value at index 1 up to index 2. And we're going to shift up the value at index 0 up to index, actually we aren't going to shift the value at index 1 at index 0, we're just going to leave that right there because 1 is less than 4. And then we're going to place x, which is kind of a temporary variable we created, into position 1. So the way we write that in code is, in this example, m was 2, and x we already had stored in a variable. And we'll say that this insert function pre-assumes that we can overwrite the position at m+1 just fine, without any issues occurring, presumably because we have already stored the value at m+1, index m+1, into the variable x. So what we're going to do is a loop from, well, first we need to figure out which index to place m at, and which index to place x at. So what we do is loop from index m down to 0, and compare the value at index I, the value, at that index that we're looping, we'll call it I. We're going to compare that to the value of x. And just like when we were doing the deck example with our hands, we will record the index, the value of the index, such that the value of the position represented by the index 1 less than that that value was less than x. Meaning, if there's a lot of words right there. If m sub I is greater than x, we're going to do our next comparison. Meaning, if we're trying to insert 4, we're trying to find the place to insert it to. Comparing 4 and 6, and 6 is greater than 4, we need to go on to our next comparison, aka the next iteration of the loop. And we can just say continue. That's going to end that iteration of the loop and go to the next one. So following this example again, let's compare 5 to 4. 5 is greater than 4, so we'll continue. Now we're over here. I is now 0. We're comparing, this right here is a typo. That should be A, same for array. And this insert m sub x should have a parameter called A, which is the array. So here 4 is greater than 1, meaning A sub I is actually less than or equal to x. So we need to write something for that logic. And essentially what we do is we need to somehow record the value of I plus 1 and then use that in our next set of logic we're going to write. So we're going to create a variable called P, which is going to stand for place, the index of the place we need to insert x into. And first we're just going to say that P is M. We really don't need to initialize it, but it doesn't hurt. We're going to say that P is equal to I plus 1, because if A sub I is less than or equal to x, we want to insert x at the position 1 to the right of I, aka I plus 1. So now we have the place that we're going to insert x at. So now that we know that, we just kind of write our we just write some shifting logic like we did right here. We were trying to insert 4 into the spot between 1, 5, and 6. We shift 5 and 6 over 2 and put 4 at 1. So the way we write that in code is so yeah, in our little example, we have that in our example, we have that m is equal to 2, because that's the index of the rightmost element in the sorted spot, and we have that p is equal to 1. So we're going to say for let I is equal to m, I is greater than or equal to p, I minus minus, and we're saying that a sub I plus 1 is going to equal what's to the left of it. So in our example, it's going to do this twice. It's going to move over 2 elements just like what we want. And then after that, there's going to be a little hole, meaning like 5 and 6 will have a little hole, meaning there's nothing at position P, which in this example is 1. So we're going to set the value at position P equal to x. So we are saying that A sub P is equal to x. So all of this right here is finding the position to insert. This is the actual thing where we do insert based on an array based on the rightmost index of the sorted portion of that array, and based on index t to insert the value x at. And again, this kind of function assumes that we can overwrite whatever's at position m+1. And this little function up here is really just a combination of find and insert. So we don't need to write these out as subfunctions. Though I don't know, if I were coding real code base, I'd like to do that. So we're going to officially define insert as P is equal to find insertion point. And this needs m, and it needs a and x. And we're going to label all of this right here. Find this as a function. This is a just sort of comment. We're going to name this function find insertion point. And this right here, we already kind of labeled as that. So we have the insert function, and essentially we just called that on every element of the array until the end of the array, starting at position 1 using zero-base indexing, meaning we essentially said that for variable I starting at position 1 going all the way until the last index, which is going to be at a.length minus 1. So we check for a is less than a.length, the largest number that will satisfy that comparison is a.length minus 1. Essentially, for each of these elements, we're going to call insert m is the rightmost index of the sorted portion, so that's always going to be I minus 1, and then the value we're inserting is the value at position I, so it would be a sub I, and then the actual array. So here we have essentially n iterations where n is the length of a, and inside of the insert function we call find insertion point and then insert. Find insertion point has n iterations, and then in Mac's case it has n iterations, and insert itself, Mac's case has n iterations. So Mac's case of the insert function is 2n, and Mac's case of, well, the best case and the worst case is going to run, n minus 1 times. So we're going to have n minus 1 times essentially 2n operations, meaning this is going to be upper bound running time of on squared, and space, we don't actually add any space besides some constant variables. So really, space is on. And I have not looked at the official solution for insertion sort. This is just what I kind of came up with, so there might be an error here. But I thought I would share my thought process. I will come back with a later video if I figure out that this is actually incorrect. And thank you for watching.